So these weeks we're going to talk a little more about clouds and precipitation. And one of the main methods we actually look at them with is weather radar. So we're going into those areas this week. So let's see what we can find with that. So first, it's how do clouds form, and then from that, why do some clouds have precipitation and other ones don't? So this is not as nice and simple as you would like it to be. We just learned that water vapor condenses. It evaporates from the ground or from an ocean, winds up in the air, lifts, gets cooled, reaches saturation. And what do you get? Condensation, right? Well, should be easy. That should be where a cloud forms. Well, unfortunately, it's not as simple as that. Clouds are visible, and they are visible because that's liquid water in the air. On average, they cover about 67% of the Earth at any given time. But every single cloud that starts pretty much will have a cloud condensation nuclei. And we're going to learn why that's important. These come out of volcanic eruptions, wind erosion of soil, forest fires, sea spray is a great one, even domestic. I'll give you a great example. When I was working in Charleston, West Virginia, the John Amos power plant had a tremendous amount of different things coming out the smokestacks at that time when I first got there. It would have a great source of cloud condensation nuclei, and you could actually see streaks of clouds forming literally just downstream from where the wind was blowing across that power plant. So you could actually visualize that power plant creating these clouds. Here's just the average percentage of clouds around the globe. Notice there's a pretty good amount of clouds around the equator. Another one off the east coast of the United States. Desert's very dry. There's our southwest United States, pretty dry as well. So when a cloud forms, it starts out as a very, very tiny water droplet. The initial size is very small. So notice that it's about 20 microns, and this will be about 2,000. This is about what? 200%, 100% more, 100 times bigger, the raindrop. So that initial cloud water droplet is curved. The tinier it is, the more the curvature around it. That's key. So we've learned that evaporation greater than condensation means water area shrinks, and condensation has greater than evaporation, water surface is going to grow. So you would think, okay, everything at 100%, right? Well, there's two things that are involved in forming a cloud. And there's one called the curvature effect. And you just saw how tiny those little water droplets are and how much of curvature there is. Well, the other is the salute effect. And that's where cloud condensation nuclei come in. So let's explore that a minute. If I have a flat surface of water, life is good. And it doesn't take very long for water to seem like a flat surface. The bigger the water droplet, the quicker it resembles a flat surface the way it works. However, cloud droplets are really tiny. When they're that tiny, it increases the saturation pressure tremendously, about 34 times actually. So in other words, I am going to require vapor pressure to have a cloud of 340%. Nothing else being around. If I have a totally clean atmosphere, I need water vapor to reach a saturation of 340%. Well, on the Earth, we're not going to get that. It's just not going to happen. So with that, here you can see it and how fast that changes. 340% for very tiny little droplets, but it doesn't take long until it's down around 100%. So you just got to make that droplet grow a little bit in order to have that happen. Well, so how do we do that? That's where the solute effect comes in. All it is, you're creating a solution. These condensation nuclei that we described a little while ago, all dissolve in that little tiny initial water droplet. When they dissolve in it, they create a solution that attracts other water vapor and creates more and more, helps that little water droplet to grow. So instead of looking at 340%, we're looking at about 100 or 101%. So it doesn't take long then for these droplets to grow. Once they get bigger, the solution becomes more pure water. But by then we're big enough that we don't care, and the water droplet can continue to grow. So unfortunately, clouds aren't nice and simple where, oh, condensation reaches 100%, we got a cloud. Now, we had to mix two other things in and mess it up for you. One is the condensation nuclei you require, and the one is the curvature effect. Curvature effect tries to keep a cloud from forming. The condensation nuclei try to help the cloud to form. So, condensation nuclei too, they can even be, like I talked about, out the John Amos power plant, but they can be other areas as well. And that's why a lot of times downstream from cities and all actually have more precipitation than upstream. There are also another type of cloud condensation nuclei called ice forming nuclei. Temperatures here got to be around -9 degrees centigrade, -10. And then ice water droplets will begin to freeze. So guess what? You see all these lakes and everything that are freezing out there. Well, if they were in a cloud, they wouldn't freeze until either they got the condensation nuclei or until it got ridiculously cold, way below zero. So there is a lot of very cold water in clouds. So these very tiny droplets have a lot of kinetic energy moving around inside of them. It keeps these water from growing into ice crystals. So, but once you start it, once you can get an ice crystal there, it doesn't take long for all these cloud droplets up there to switch over to ice. But if you got down to -39 degrees centigrade, or almost exactly the same, -38 degrees Fahrenheit, called the Schaefer point, everything's going to freeze. So yes, you get high enough clouds, cold enough atmosphere, you can get this without any ice. Otherwise, you're going to need these condensation ice nuclei to make it happen. And once ice forms, then these ice crystals also act like ice nuclei and help other ice embryos to form. So it's a cascading effect. Once you get one, you develop other. Now, why in the world doesn't all those clouds droplets fall to Earth? Well, guess what? Air resists that. And because of that, you got to get more and more bigger and bigger droplets. And once it gets big enough, then it will fall. And that includes whether you have snowflakes or water droplets. So when they fall, gravity is going to pull them down like it pulls us towards the ground. And there's friction of the air, and they're going to reach what we call a terminal velocity. They can't go any faster than that point. That's because there's a balance between the gravity pulling them down and the friction of the air pushing them up. So how do raindrops form? Because we've got the clouds now started. How do we go from a cloud to where it's going to precipitate on you, make you wet, cold, miserable? Well, one method is collision coalescence, and another one is Bergeron-Finn Dyson. Collision coalescence works when the cloud temperature is above freezing. Bergeron-Finn Dicing works when there are ice crystals in the cloud. So, if I was in the middle of summer and the temperature was really hot and hot a long way up into the atmosphere. Say you were in the tropics, for example, everything would be water in that cloud. So if I have water, one water droplet might get a little bigger than the others and start to fall. Well, what happens when it starts to fall? It hits other droplets. Oh, they get a little bit bigger then. And everything continues to grow until it gets big enough to become a raindrop and hit the ground. That's all we're saying here. Now, ice. Almost every cloud starts as ice crystals and then develops precipitation from that. And that means that Bergeron-Findyson effect begins almost all precipitation where we live. So, we learned something last week. You learned that saturation vapor pressure is higher over water than it is over ice. Ice has less kinetic energy, so it is going to tend to have a slightly lower saturation vapor pressure. So if you form an ice crystal, there is a pressure gradient that develops between that ice crystal and the water droplets. So water is going to flow. Those water vapor flows from the water droplets into the ice crystals, and the ice crystals grow. So that is how these ice crystals become bigger and bigger and eventually fall out as snowflakes. Almost all precipitation in our area begins as that. So once they leave the clouds, then you might have dry air around it, whatever, that's going to tend to want to vaporize that water. So that's why if it's a really cold, really, let's just say a really hot day, very dry, and you see all these clouds above you, and you think, wow, it's going to pour down the rain. And you see this little streaks like this in the sky, but they never get down to the ground, or maybe just one big drop does here and there. The reason that happens is they've evaporated. So there are different types of precipitation. Rain, raindrops, drizzle is very tiny rain. Snowflakes, and guess what? They're all shapes and sizes. That's why when somebody is telling you how much snow is going to fall at your house, one of the things they're actually trying to figure out is what type of snowflake you're going to haul. If I have thin plates or prisms or needles, they're not going to accumulate as fast as a dendrite. So I am always looking for figuring out which type of snowflake I'm going to have, and then from that, estimating how much snowfall you're going to get at your house. Maybe I figure out, oh, you're going to get a ½ inch of precipitation. Normally that is 10 to 1. So 5 inches of snow. But if I have little ice crystals, like prisms, that are going to be falling, well, then that 10 to 1 might go down to 2 or 3 inches. If I have dendrites, maybe it's more like 5 or 6 or 7 inches. If I have a mix, maybe it is 5 inches. So you can see, knowing what type of ice crystal is going to form can make an impact on how much snow you get. So if I said everything starts as a snowflake up here, Bergeron-Findyson, we know that warm air lifts over top of cold air. So as a warm front's approaching your area, warm air is lifting up over that very cold air. So you wind up with, oh, precipitation begins to fall. And we'll say we're well out ahead of that warm front. So here comes the snowflakes hitting a pocket of temperatures above freezing. Well, those snowflakes are melting. Then we have a bigger pocket of below freezing air at the bottom. Now they're freezing back into sleet. If I have only a little bit of freezing air, they go into ice. And eventually, as I get closer and closer to that warm front, temperature goes above freezing at the ground and it just is all rain. But they did start out as snowflakes up here. Hail, all it is super cold water droplets freezing when they get lifted so high. If they're in a thunderstorm, there's a tremendous updraft in that thunderstorm. And these water droplets freeze with a whole bunch of super cold water that's been pushed way up into the atmosphere. They bump into each other, they keep collecting each other, and you wind up with a large hail. As these hail pieces may fall back in the rain shaft for a little bit, get picked back up in the cold updraft. So they keep refreezing and you get layers on them. And that's how hail forms. Freezing rain, we just saw it. Temperature goes above freezing for a while, but then down to the surface. Little layer. The most extreme case I ever saw was in Sterling of this happening. We had freezing rain, a temperature of 15 degrees. Yes, it was coating everything. As soon as the rain hit, everything froze. But not even 1,000 feet up, the temperature literally was 45 degrees. So we had a very, very, very thin freezing layer. Okay, radar is a great way to detect precipitation, even clouds. We used it all the time, and it has two different modes it operates in. Reflectivity mode. So if I send a signal out and it bounces off a raindrop and comes back, that's reflectivity mode. All it's doing is how many raindrops are in a little area. The more raindrops, the more ice or snow, the more the energy is going to return back or be reflected. So it indicates heavier precipitation. And if you have hail, it even looks different than that. Much, much more intense reflectivity return. Velocity mode. Here's where I'm looking at frequency changes. We've all heard a train go by, a car go by, whatever, and the way it sounds, it's a little different. That's what we're doing with these raindrops. When we go send it out, if the raindrop's moving towards us, it has one change of frequency. If it's moving away, it has another. And the more it's moving, the greater that change. We know what frequency we sent out that pulse of energy at. How that energy changed is what determines the velocity. Also, I wanted to point out, radar sends out a pulse and listens, but radar starts out at a half a degree. That big dish you're seeing right down here starts out literally pointing at 0.5 degree elevation. So in other words, it's not coming out perfectly horizontal. It's just a little bit of a tilt up. While it rotates, and every time it rotates, it changes its elevation. And if it's in severe weather mode, it'll get all the way up to 19.5 degrees. The idea is to look higher and higher in the storm. So we're getting a complete picture of what the whole precipitation and all is happening. And if I'm doing this in a severe weather event, it takes about 4 minutes to scan the entire atmosphere. Now, if I'm not caring a whole lot, if it's just normal light rain, maybe it'll stretch out to almost 8 or 9 minutes to do this. So you can see we actually get a whole complete picture of the atmosphere around the radar in a 4-minute time in severe weather, longer in less. And here's where we're showing that Doppler frequency change. So let's look at it. This is a cool one. Here is a hook echo. All that is where there's a low pressure right in here. And with that, here's velocity. Notice how they circulate over. One is right next to the other. So literally, I'm having velocity moving one direction and the other. So we have counterclockwise circulation here. And that is where the tornado is. And if you pointed over here, that would be right in this area of curve and also an area of very intense precipitation. These tend to have that. The final thing I wanted to point out is when we've gone to dual pole radar, dual pole gives us both a horizontal and a vertical picture of these little droplets. So when I can do that, I can start telling, oh, this is rain. No, that's snow, that's hail. Or in the case of a tornado, I can say, oh, this is junk up in the air that the tornado stuck up. That's what dual poles give me a benefit of. You can see here as a hurricane coming in. You can actually see the bands and structure here. Tremendous winds blowing around it. Phased array. I would love to have it. I got the privilege of playing with it in Norman, Oklahoma once. All it is, it takes continuous pulse at every elevation. Instead of that antenna rotating, it doesn't have to. Different spots on it will go up to a different angle, and it continuously receives data. So when that happens, instead of taking 4 minutes to do a scan, I get it instantly. Always. So I'm looking, I can pick up things a little quicker. So how do we measure precipitation? One of the biggest and simplest ways is tipping bucket. That's what ASOS uses. All it is a little thing that holds rain, tips every time the weight reaches what would be 1/100th of an inch of rainfall. So the more tips, the heavier the rain's coming, the more rain. Snowfall. This is one of the most difficult things to measure. You have a board placed out there and you measure every so many hours how much has fallen on that board. And you remove it and then redo it again. But it can be difficult to get an accurate measure of snowfall because wind might blow some of it off the board. Maybe it melted a little bit on the board. All these different things can impact that measurement. So we just talked about weather radar being able to detect these raindrop sizes. Now that we can detect the size better, we can actually estimate the amount. We're getting more and more estimates from precipitation totals from that. Here you can actually see estimated rainfall from a storm down in New Orleans. 1.5 to 2.5 inches. And here's some places up in the white, 10 to 12 inches of precipitation out in here. All right, final part. There are different kinds of clouds. Cirrus clouds, wispy, almost always ice. Stratiform, a layer. Cumuliform, humps. So most high clouds are in the form of cirrus, but you can have a stratus, a thick layer of cirrus, or cumulus up there where there's actually bumps. And that's a day when you don't want to fly too well because you're probably going to bounce around up high. Middle clouds, same thing, altostratus, altocumulus. Here are low, stratocumulus, stratus. Finally, here's the cumulus. See how the little nice puffy ones? Here's a little bit cumulus congested. Might just be out being ready to make a more like a towering cumulus cloud. Now you finally have cumulonimbus. And you can see here, these cumulus bubbles on satellite show up. But notice there's nothing over the lakes. The lakes are very cold at this point. And that's why there was no clouds over the lakes whatsoever. Sometimes you do get cloud streaks over the lakes, especially in the fall and early winter when the lakes aren't frozen. And you can see them develop on the lakes and move down, bringing precipitation and snowfall to areas. Interesting cloud pattern, lenticular clouds. This is a middle cloud that forms circular right over a mountaintop. It'll sit there all day. And then you have the other ones where the winds hit the mountain, move up and down, and they form lenticular clouds downstream, mountain wave clouds, because they'll lift up. Hey, I reached high enough, I accumulate, I can condensate the atmosphere, and here comes a cloud. Oh, I'm going to drop back down. I'm warming. I evaporate. Then another one forms. If you're a pilot flying a small aircraft, you wind up watching for these when you're flying into mountain airports because you don't want to get in one of these. They tend to have very strong up and down drafts and really can cause tremendous turbulence. Kelvin-Helmholtz waves. All they are, it's very dense cold air at the bottom, very less dense warm air at the top. I used to watch these on a mountain chain in the Susquehanna River in Middletown. You would see them form on the mountains after a strong thunderstorm would go through. Fog, condensation occurring at ground level. In West Virginia, I worked in West Virginia for a number of years. If you look in Charleston, West Virginia at the airport, you'll notice there's two river valleys right by it. We would always watch for fog to begin forming in the river valley And part of the criteria we had to figure out is the fog going to get dense enough and high enough up to infect the airport. Sometimes it did, sometimes it didn't. That was always part of the forecast issue. You can see here where the fog formed in the Grand Canyon and actually stayed there for 4 days. So if you had been wanting to hike up and down the Grand Canyon, you wouldn't have had a very good time. Fog can advect. I was at a football game, a high school football game at Florida State one time. It's only about 20 miles to the Gulf right there. That day, warm air was coming in off the Gulf of Mexico, and the temperatures where the game was, where we were still cooler. Hit the ground, fog began to form, and as that air advected in from the Gulf, it kept forming clouds. It got thicker and thicker, and by halftime, I couldn't see across the field. And mountains can cause fog. A classic case in the Appalachians is if you're driving Interstate 64 in Virginia on the one side, and you're coming up the mountain to the west of Charlottesville. Many times fog will form on the east side of that mountain as the wind moves from the east, or the water up forms up that slope. You run right into the fog and you wind up, there's been numerous accidents in that area because of it. So I hope you got a little bit out of this. I know I probably went too long, but let me know if you have any questions.